Hi professors, I'm Jun Yang, and today my group and I will be presenting our assignment 1. I will now be sharing about our abstract engine structure. Our engine is built on a class-based architecture, which, while less flexible than a component-based approach, gives us clear, direct mappings to OP concepts, ideal from a learning standpoint. The architecture is split into two distinct layers. The engine layer holds all the domain-independent systems, things like our managers, as well as the abstract entity classes and behavioral contracts. Critically, it contains no simulation-specific logic. The simulation layer then builds on top of that is where the concrete implementations like our specific scenes, UI entities, and input sources like mouse and keyboard. The key goal here is simple. We should be able to create a completely new simulation without touching the engine at all.
Now let's run through the program flow. When the game engine initializes, it creates a scene manager, input manager, and audio manager. It also initializes and registers audio and scenes. Then it starts the simulation scene. Game engine renders at each frame, updating the input manager and scene manager. Scene manager also calls render, and the game engine also posts for global input. Input sources are poked, and the active scene updates to check for entity movement or collision or remove entities. The active scene also passes on the render to the entity manager, which then triggers the draw method on entities. Simulation logic augments scene behavior based on these updated information, and the process repeats. Disposal propagates from the game engine to individual entities. The exact flow is shown below. Now let's look at our innovations and enhancements. The first is scene cycling. Scene transitions with two distinct data structures. This allows for the overlaying of scenes for pause menus or game over scenes. Many scenes can also be added without changing transition logic. Next, our separate entity hitbox structure means that hitboxes are independent of visual representations. This enables innovative collision behaviors. We also implemented input abstraction. Input state maps device inputs into common input states, and this allows extension to new devices or different input combinations. In summary, our enhancements improve flexibility and alignment with OOP principles.
Now, let's dive into our core system, starting with how we manage the simulation environment. Our scene manager uses two primary data structures, a stack to handle the active scene laptop and support overlays like settings menus, and a list for cycling through game scenes. This allows us to manage the entire scene lifecycle and transition seamlessly. Moving inside the scene, the entity manager acts as a central registry, storing all active entities in a map for efficient access. To enforce encapsulation, the manager protects the internal collection and only provides an unmodifiable view, ensuring that entity lifecycles remain under strict control. On the logic side, our movement manager receives the entity map and applies specialized movement to objects marked as movable. Simultaneously, the collision manager performs pairwise checks on hitboxes, delegating the heavy math to a dedicated collision detector utility. If a hit is detected, it delegates the specific reaction back to the entity itself. Our input and audio managers provide critical abstractions. The input manager maps device-specific signals into common input states, making the engine compatible with various hardware without changing core logic. Meanwhile, the audio manager centralizes sound storage and volume control, decoupling audio lifecycle management from individual scenes.
Our entity hierarchy starts with the baseline abstract entity class, which is extended to the abstract movable texture object class as a template for objects in our first simulation scene. The bucket, droplets, and wind, all of which are movable and collidable texture objects. As for the second simulation scene, we have a player class which extends entity and implements movement and collision, and a rectangle wall class which extends entity and implements collision. Our structurally simple entity hierarchy reduces code duplication, which allows for specialized behavior.
So going over the key implementations of abstraction and encapsulation. For abstraction, we've implemented three abstract classes, which are entity, scene, and hitbox. As for encapsulation, the entity manager protects the entity collection by making the internal linked hash map private and only allowing a unmodifiable view through the public getter method, which prevents external modification from other methods. Next, to prevent hitbox shape clash, a movable texture object enforces non-null for a set hitbox method, and the player circle only accepts circle hitbox. Finally, for entity lifecycle control, entity active is private, and also there is no setter to reactivate or dispose entities. For the implications of inheritance and composition, we have an entity-based class, as well as a movable texture object class, which is a reusable texture, movement, and collision implementation used by the droplet, bucket, and wind objects. Also the scene-based class, which contains a common update pipeline. Finally, for the hitbox class, it allows for easier extension for new hitbox types in future. For composition, the entity manager owns the internal entity storage. The input manager owns input state objects. The input manager will create new input state objects within itself via add input source. Finally, each scene owns its managers and creates managers for entity, movement, and collision.
Our key interfaces, iMovable and iCollectible, mark entities that can move or collide. This lets our manager handle movement and collision generically without needing to know the concrete classes. Similarly, input source abstracts where input comes from, so our engine can support different devices without touching the abstract engine. For abstract classes, entity is the base for all objects. Movable texture objects extends it as a template for dynamic actual objects. Scene defines lifecycle methods that subclasses must override. And hitbox abstracts collision shapes to keep collision management generic. For polymorphism, we apply method overriding in two key areas: scene lifecycle methods, which concrete scenes must override to define their own behavior, and our movement and collision systems, where the actual method executed depends on the concrete class at runtime. For method overloading, Droplets implements multiple constructors for flexible instantiations, and entity overloads two no-op draw methods, one for shapes and one for textures. Thank you.
Now let's run through our UML diagram. We start with the game engine, which composes of an audio manager, an input manager for global inputs, and a scene manager. The scene manager contains multiple scenes, and each scene has its own entity manager, movement manager, and collision manager. The entity manager of each scene contains the entities of that scene, and as shown, these are our 3 scenes in our simulation. Our movement manager and collision manager updates every frame. The movement manager updates the position of the entity, while collision manager checks for collisions. The collision manager outsources the collision detection to a package private collision detector class, which contains the geometric logic required to detect collision. We did not go one step further to ensure that the collision detector class does not have to be changed if a third hitbox is added. This is because we do not have plans of adding a third hitbox, and hence, further advancing this implementation would mean that we add additional complexity with no real practical benefit. If collision is detected, the collision manager delegates the resolution of collision to the entities themselves. Now let's move on to our input management system. Our input manager contains input sources and input states. It composes of input states, which does what it says. It stores the input states, and it also defines methods that allow for the retrieval and modification of the states. This retrieval and modification is done by input source implementations. We have an input source interface which allows the implementation of multiple input sources, varying from different device types and also different input combinations, with the option to disable certain inputs. This aligns with the open-close principle, as new input sources can be added without having to modify the input management system. Similar to our other managers, the input manager constantly checks for updates to the input states, which are modified by the input sources. Our audio manager is rather simple. It has map data structures which stores sound effects and music tracks. We define methods to load and play sound effects and music tracks, set their volumes, and also dispose of them comprehensively. Now let's look at our entity implementation, specifically how they implement collision and movable behaviors, and how collision is detected. Our entity abstract class is the baseline for all entity objects in our game engine. For defining behaviors, we have our collision interface and our movable interface. We also have an abstract hitbox class. This extends to a rectangle hitbox and a circle hitbox. These hitboxes contains the elements required for collision and define methods that allows for collision behavior. Now let's look at our simulation's entity hierarchy. The most simple set of entities are the user interface elements, like the button, volume slider, and the static texture entity, which is used to implement our background. These classes merely extends the abstract entity class. All of our other entity implementations have collision logic, hence they contain an abstract hitbox class, which could be a rectangle or a circle. Let's look at a rectangle wall. It extends entity abstract class, however it only implements the collidable interface, as it does not need to move. Our player circle class has to move and collide, and hence it implements the collidable interface and the movable interface, while extending entity abstract class. Next, we have our other abstract class, which is movable texture object, which implements collision and movement and extends the entity abstract class. We chose to implement this abstract class because we have multiple implementations of it. For example, bucket, droplet, and wind. They all need to collide, they all need to move, and they all are texture objects. Now, let's move on to the code demonstration. Let's start by running the code. Here we present our first simulation scene. We have a droplet catching simulation with a wind object that is able to blow the droplets around. As the scene loads, the background music and droplet sound effects are loaded. Here we showcase our ability to detect rectangle-to-rectangle collisions. 2 input sources are loaded, one tied to the bucket, one to the wind. And the game is won by catching 100 droplets. The user can press R to restart the game at any time. Once we catch 100 droplets, the game is won and the droplets are removed. Our texture objects are designed to respect the screen boundaries. Before we go to the pause menu, let's look at the current amount of droplets catched and the current time. We press escape to go to the pause menu. In the pause menu, there are 2 input sources, one to adjust the volume with up, down, left, right keys, and one to adjust using mouse clicks. And we also have a resume and quit button. The resume button continues the game. As shown, the state of the scene is saved as the number of droplets catched and the timer remains unchanged. Now let's move on to the other scene. We have showcased the ability to transition between scenes and switch audio between scenes. The yellow circle is tied to a mouse input source, and our green circle is tied to the arrow keys. Here we showcase our ability to detect circle-to-circle collisions and also circle-to-rectangle collisions. When the circle touches the rectangle wall turns red. When both circles touch, both turn white. This shows the ability to detect multiple collisions at once. Our circles respect the boundaries of our screen. To exit the simulation, we go to the pause menu and click the quit button. This concludes our code demonstration. Thank you.